absolute error, in division. This is you having a quotient of two numbers, for example, A over B, that is the quotient of A and B. So if you want to get the maximum, I want to get the absolute error, say that the absolute error or the maximum possible error there is equal to a half into maximum value minus the minimum value. Maximum value minus the minimum value. So if you get the maximum value in the quotient, you have to get the maximum value in the fraction when dividing two numbers, and you're interested in getting the maximum value. What you do, you make the numerator very big and you make the denominator very small, and that's how you get the maximum value in the quotient. You make the numerator very big and then you give it a very small value, then you come up with the minimum value. Then if you have to get the minimum value, here, what you do, you make the numerator very small, that is by minimizing it, and make the denominator very big, that is the big maximum. You maximize the denominator and you minimize the numerator, then you come up with the minimum value of the expression in the quotient. Now we can add there the absolute error in multiplication. Absolute error in multiplication, if you're multiplying two numbers. This is you're having the A times B, that is the product of the two numbers. So if you get the maximum value, in the product, you make the A very big times B very big. That is maximizing both of the values. That is in the multiplication. And if you get the minimum value, the result minimum value, you get the A, make it very small. That is A minimum times B minimum. That is minimizing the two numbers. You get one, you make it very small, and the other one very small. Then you multiply the two small values, you get the result which is very small. That is the meaning of the minimum, minimizing minimum value of the product. So we are given this three decimal numbers. X is equal to 0.25, y is equal to 0.150, then the z equals to 2.064. Then you want to find the absolute or the maximum possible error which is made this expression here. The expression is z over y minus x times z. So we are combining multiplication, division, and subtraction. That's what it is in the expression. So what we do before we commence in getting the absolute error, first of all, we get the maximum possible errors in those numbers. We get the maximum possible error. The maximum possible error in n, a maximum possible error in n, x, and we call it the ex. And x has the two decimal places, 1, 2, so it will be 0.5, and then for negative 2, which is 0.005. That is the maximum possible error. Then you have the maximum possible error in y. We have y has three decimal places, 1, 2, 3. So it will be error in y equals to 0.5, and then to negative 3 as the decimal places. So it will be 0.0005. Then we have the maximum possible error in z, we can call it ez, and this is 0.5 and the number of decimal places. It has 3, so it will be 10 to negative 3 is 0.0005, and that is the maximum possible errors which are made in those decimal numbers. So if you get the maximum and the minimum values, We use the principles which we discussed before. We get the maximum value of that expression. If you get the maximum value of the expression, this expression here, which is z over y minus x. Then what we do, since we are having, first of all, we make this one here a very big value. This is maximum, and what we're taking away, we make it very small. And this is the product of two numbers. If not to minimize them, you make sure this one is minimum, and also this one here is minimum. And this one here, this is a quotient of z over y. So if you want to get the maximum value here, you make sure that the denominator is very small and the numerator is very big. That's when you get the maximum value here. So let us see, this one here will be the z over y. This one here you make it maximum, and what you are taking away, you make it minimum. The xz should be minimum, and that way you will come up with the maximum value. And if you have to maximize this one here, you make the numerator, because this is a quotient of z and y. So what you do, you maximize the numerator and make the denominator very small. These ones here, you minimize both of them. So this one here will be now z maximum over y minimum minus x minimum times x minimum times y times z minimum. That's how you minimize. So the maximum value here, you make this term maximum, and what you're taking away minimum. So you get, how do you maximize z? You make z maximum, you get the z plus its error, and that one will be the z, it is 2.064 divided by minus, plus, because we are maximizing it, plus its error, which is 0.0005, then over z, and z should be minimized because we want to get the maximum outcome there. So y will be 0.150 minus its error, which is 0.0005. That is the maximum possible error in y. 3 decimal places, 3 zeros there. Then minus, what you are taking away, you make it very small, that is x minimum or z minimum, and so this is the minimum x is 0.25, making it minimum is minus its error, which is 0.005, then times z should be minimized, which is 2.064 minus its error, which is 0.0005. Then we use our calculators here to come up with the values. Maximizing, saying that this term should be maximum, this term should be minimum. Because what we're taking away should be very small. This is the product of two numbers, minimizing them, minimize x, minimize z, to come up with a small value. So what we have done here, minimizing z, minimizing x, minimizing z. We get the product, we get a minimum value and weight. That one a minimum, 0.50556. Then this one here, the z maximum, you make z very big. You can make a y very small. That is adding z plus this error divided by y by this error, that is minimizing. And when you come up with 13.094, you maximize the number of decimal places. You use at least 4 decimal places for, unless if the question has specified that you use maybe for 3, but if it has not been mentioned, you stick to 4 decimal places for accuracy purposes. The more number of decimal places, the more accurate your work becomes, your result becomes more accurate. So when you take the difference of 13.30384, then the minimum, you get the minimum value of the expression. You get the minimum value of that expression. You make sure that this term is very small. That is, you make the z over y minimum, make it very small. And what you are removing away, you make the xy, the xz, you make it very big. That is how you come up with the maximum value. What you are having, you make it very small, and what you are taking away, you make it very big. So, and how do you do that? This one here, you make it very small and the denominator very big. That is now minimizing the whole of this term. It will be Z minimum, very small, and Y maximum. It's the reverse of this one here. Here Y was maximum, Z was maximum, the numerator, then the denominator was very big. So that you come up with a very big value. So here if you're minimizing, you make the numerator very small and the denominator very big, that is maximizing. Then minus the maximum value here, you make both X maximum times Z maximum. What we're taking now, what should be very big such that you make with a minimum value. So the minimum value here, the minimum value will be 2.064 minus the minimizing Z 0.0005 over maximizing Y will be 0.150 plus the error 0.0005. Then minus is X make it big 0.25 plus error 0.05 times Z, which is 2.064 plus the error maximizing, which is 0.0005. Then we will see, use our calculators. So the maximum value, we have minimized the Z by subtracting it from its error minus Z. Then maximizing the denominator, error plus Y value. Then this one here is minimum. Here, minimum. The product should be minimum. It should be maximum. Sorry, maximizing X, maximizing Z. That is X plus its error, Y, Z plus its error. So when you use the calculators, the first term here giving us 13.71096, then the second term here is giving us 0.526. So when we subtract it to the minimum value of the expression is 13.18451. Use as many numbers as possible for accuracy purposes. Then we get down the absolute error. The absolute error, we say that it is a half into the maximum value minus the minimum value. That's how we get the absolute error. The maximum value minus the minimum, so it will be a half into the maximum value. We obtain the maximum value as 13.30384 minus the minimum value of the expression, which is 13.18451. That is when you take the difference there, with the error which is 0.059, and that is the absolute error which was committed in that expression. So the absolute error is in that expression is a combination, because there was an error in X, an error in Y, and error in Z. Then when you combine this term here, Z over Y, X minus Z, so this is the whole expression. So to get the maximum error which is made in that expression, you combine. First of all, we get the absolute errors in the given decimal number. Then you come up with maximizing maximum value. And this is the difference of two terms. This term here you make it very big, and this is Z minus Y is a quotient. You make sure the numerator is maximum, the numerator is minimum. So just get the maximum term. And then minus the minimum, what you're taking away, you make it very small, and it's a product of two values. Minimize this one, maximize that one. Then you come up with the value. Then minimum value here, make sure that this one here it is minimum. And how you minimize, you make Z, the numerator very small, and the denominator very big. And what you're taking away, you make it very big such that you make the smaller value minimum. And how you minimize this one and make this one here very small, this one that is very small. Such that when you substitute, you come up with the value. Then you substitute in the zero statement, or the absolute error is equal to a half maximum value minus the minimum value. Look at the relative error. The relative error is the absolute error, or that is the maximum possible error in the expression, over the exact value, or the relative error is also defined as the absolute error over the inexact value or the approximated value. And in some authors, you find this term here, the approximated value of the expression, where they are using it as the working value. The working value is either the absolute error over the approximate value or the working value, or the absolute error over the exact value of the expression. Both of those ones will come out, will lead us to getting the same correct results. And absolute error over the working value or the approximate value. So we can also what we call the percentage error. And the percentage error here, it is obtained from the relative error times 100. Relative error over the approximated value of the expression, then times 100%. Absolute error, which is the relative error times 100%. And percentage error is relative error times 100%. And if we were to break it down, the percentage error is relative error times 100%. But from the definition of the relative error, the relative error is the same as the absolute error over the approximate value or the working value. So here you can use it. The relative error is the same as the absolute error over the approximate value or the working value times 100%. We shall see how to get the working value and the absolute error, and so we can calculate the percentage error. Let us use an example to illustrate this one. If I give the two decimal numbers, for example, you have A is equal to 2.5 and you have B is equal to 1.05. These are two decimal numbers, and we want to calculate the percentage error in the quotient A over B. So if you have get the percentage error there, what we do, we first obtain the absolute error, then after we calculate the percentage error. Now, first of all, we get the absolute error equals to a half into maximum value minus the minimum value into the minimum value. And then the maximum value of the quotient, the maximum value of A to B. Now again, the A will make it very big, then you get B and you make it very small in the quotient. And how do we do that? We get the A plus its error. A has one decimal place, so its maximum possible error. It will be 2.5 plus the maximum possible error in A has one decimal place is 0.05 over B. B minimize it. You get the value of B, which is 1.05 minus its error, that is minimizing. That has two decimal places, so it will be 0.005. That is minimizing. And you can use our calculators there, get it. We are maximizing A maximum over B minimum, so we maximize A, minimize A. So when you use the calculators, you come up with the Then we get the minimum value of the expression. And if we get the minimum value of the expression, we make A very small, that is A minimum. Then we make B very big, that is B minimum. We have B maximum. Also we are minimizing. We make the numerator very small and the denominator very big. And how we do that? We get the A 2.5 minus its error, maximum possible error, over 1.05, that is the value of B. We're making it a maximum, so plus 0.005. That is just the two decimal places, 0.005. So we can use the calculator there to get minimizing. We have minimized A by getting A minus the maximum possible error as one decimal place, as 1 0 here, two decimal places, 2 zeros there, so 0.005. Then when you compute, you come up with 2.32227. That is the minimum value. So now we can look at now getting the absolute error. Absolute error here will be a half into the maximum value, which is 2.44019 minus 2.32227. Get the absolute error, get the maximum value from the expression minus the minimum value from the expression, then times a half. And we come up with 0.5896 as our absolute error. Remember, what we want to get is the percentage error, and how to get the percentage error there. We have the absolute error from the formula here. The percentage error is equal to absolute error over the approximate value or the working value. And how we get the working value? We get the actual expression, we get the working value. Working value or the approximated value. We get the expression A over B. We substitute the true values of A and B, which is 2.5 divided by 1.05 to get the working value or the approximated value. So we 2.5 divided by 1.05, and this one is giving us 2.38095. That is the working value. That's the working value. So to get the working value, you get the statement the way it was the expression A over B. Then you get the given values, these values which are given, the A and B, and you substitute them in without maximizing or minimizing. You substitute them in the expression. Then we come up with the working value or the approximate value. Then we get the percentage error. From the definition is equal to absolute error, which is 0.05896 over the working value, which is 2.38095 times 100%. Then when we use our calculators there, we are having the absolute error over the working value or the inexact value. You find in some quarters what they're using as inexact value instead of the approximate value, but it's all mean the same thing. The working value or the inexact value. You get the expression and the given values without maximizing or minimizing them and substituting them in the expression, and that is the working value. So the way this percentage error, when you use the calculator there, you have it as a 2.476% as the percentage error, which was made when those decimal numbers were rounded off to those given number of decimal places. That's how we obtain the percentage error.